So in the previous class, I started work for energy. I was discussing about the work done by the force of gravity, calculation of the work done by force of gravity on a body when the body undergoes a small vertical displacement near the Earth's surface. Small displacement is in the sense small compared to the radius of the Earth. So as I discussed, if the body falls vertically downwards, so that it undergoes displacement in the direction of force of gravity, and if the body falls to a vertical height h near the Earth's surface, then work done by the gravitational force of the body can be written as mgh. The height h is very small compared to the radius of the Earth. Same conclusion holds good irrespective of the path followed by the body. Suppose if you consider a block of mass m which slides down a fixed inclined plane, with some angle of inclination, say alpha to the horizontal. So let us consider a block sliding down a fixed inclined plane with vertical height h but angle of inclination alpha to the horizontal. So I am not going to solve any problem at present. I am not discussing a problem. I am just only discussing how to calculate the work done by gravitational force on the body in different situations. The weight mg acts vertically downwards. Of course, normal reaction force on the block by the inclined surface acts perpendicular to the inclined surface and directed away from the inclined surface. Now the direction of this, the block slides down the inclined plane. Then the direction of the displacement of the block is parallel to the inclined surface in the direction of its motion. The line of action of normal reaction is produced backwards. The angle between the line of action of normal reaction produced backwards and the weight mg will be same as the angle of inclination alpha of the inclined plane to the horizontal. So in this case, the angle theta between the direction of the gravitational force and direction of the displacement, the angle theta between the direction of the gravitational force on the body and direction of displacement will be 90 degrees minus alpha. So work done by constant force F bar when the body undergoes linear displacement S bar is given by dot product of force and displacement vectors. So work done by magnitude of the gravitational force into magnitude of the displacement into cos theta. So work done by the gravitational force on the body, you can write magnitude of the gravitational force is mg. Theta equal to 90 minus alpha. So then cos 90 minus alpha is sin alpha. So work done by the gravitational force on the body can be written mg sin alpha into s. S is the magnitude of displacement parallel to the inclined plane. So when the block slides down the inclined plane, suppose if it starts from rest from the top of the inclined plane, then when it reaches the bottom of the inclined plane, magnitude of the displacement will be equal to the length of the inclined plane, which is usually denoted by L. So when the block reaches the bottom of the inclined plane, the magnitude of the displacement, I mean if it starts from the top of the inclined plane, then when it reaches the bottom of the inclined plane, magnitude of the displacement can be written as equal to length of the inclined plane. If h is the height of the inclined plane, then sine alpha you can write h by L. So work done with the gravitational force of the body. The body slides from top of the inclined plane to the bottom of the inclined plane will be called mgh. That means work done with the gravitational force of the body, and the body falls through some vertical height, depends only on the vertical displacement in the direction of force of gravity. Does not depend on the actual length of the path along which the body has actually traveled. It means suppose if the body slides down another inclined plane, suppose if the body slides down another inclined plane of different length and different angle of inclination to the horizontal, but same height h. Even in this case, work done with gravitational force of the body when it slides down from top to the bottom of the inclined plane, second inclined plane is also equal to mgh. So work done with the gravitational force of the body when the center of gravity of the body falls through a vertical height h near the Earth's surface can be written as equal to mgh irrespective of the path followed. That means some problem the block may fall freely under gravity through vertical height h. So for example, the block may slide down the smooth inclined plane. So in some of the questions, the block may slide down a curved track. If a block suppose slides down a curved track starting from the top of the track, so when it reaches the bottom of the track, we can say work done with the gravitational force on the block equal to mgh, where h is the vertical height through which the block falls. That means the work done with the gravitational force of the body depends on the vertical displacement of the body along the direction of force of gravity, but does not depend on the actual length of the path along which the body has traveled. Even if a block is suspended by a string, so that upper end of the string, the top end of the string is fixed, like in a simple pendulum. The block is pulled to a side and released, so that the block swings in the vertical plane under influence of gravity. Then work done with the gravitational force on the block. When the block, center of gravity of the block falls through a vertical height h, as it falls from one position to another position, equal to mgh again. So in general, when a body of mass m, I mean the center of gravity of a body of mass m falls through a vertical height h near the Earth's surface, then the work done by the gravitational force of the body will be written as mgh, irrespective of the path followed. Irrespective of the path followed. Here h is the vertical height to which center of gravity of the body falls. The same way, when you calculate the work done with the gravitational force of the body, when the body is sliding down the inclined plane or inclined path, we usually resolve the weight mg into rectangular components parallel to the displacement and perpendicular displacement. The body has a displacement down the inclined plane. The component parallel to the displacement as magnitude mg sin theta. Here theta means the angle of inclination of the inclined plane to the horizontal. The component perpendicular displacement is mg cos theta, which is opposite, which is balanced by normal reaction. So in general, work done by constant force on the body can be written as product of the magnitude of the displacement and component of the force in the direction of the displacement. Work done by the force is positive and the force has component in the direction of the displacement. So work done by the gravitational force on the body can be written as, when the body is sliding down the inclined plane, I mean product of the magnitude of the force of gravity in the direction of displacement and magnitude of displacement, or mgs sin theta. The body slides from top of the inclined plane to the bottom of the inclined plane. The magnitude of displacement, we write length of the inclined plane, and sin theta you can write h by L, where h is the vertical height of the inclined plane. So work done by gravitational force will be written as mgh. Suppose if the body is moved up along the inclined plane, or the body is suppose projected from the bottom of the inclined plane with some initial Austrian left, so that it moves up along the inclined plane. We're not solving any problem at present. Again, I'm telling we are only discussing on how to calculate work done by gravitational force of the body in different situations. And alpha denotes the angle of inclination of the inclined plane to the horizontal. The weight mg of the block acts vertically downwards. The normal reaction force of the block by the inclined surface acts perpendicular to the inclined surface and directed away from the inclined surface. The weight mg can resolve into two rectangular components parallel to and perpendicular to the displacements. The component mg cos alpha acts perpendicular direction to the displacement. The component mg sin alpha acts down the inclined plane opposite direction of displacement. In general, work done by force on the body can be written as work done by the component, sum of the work done by two rectangular components. The work done by the component mg cos alpha, you can say 0 because it acts perpendicular to displacement. The component mg sin alpha acts opposite to the displacement. So work done by the component mg sin alpha, you can write minus of mg sin alpha into s. Some of the students may get a doubt, why not we use the basic equation f bar dot s bar? Because work done by constant force on a body is given by f bar dot s bar. Even by that way, you get the same conclusion. So here direct for the displacement up the inclined plane. So in this case, the angle theta between the force mg and direction of the displacement will be 90 plus alpha, where alpha is the angle of inclination of the inclined plane to the horizontal. So even if you go by that definition, f bar dot s bar, the gravitational force mod of f bar into mod of s bar into cos theta. Magnitude of the gravitational force equal to mg here. Magnitude of displacement will be denoted by s. Theta is 90 plus alpha. So cos 90 degrees plus alpha, we can write minus sin alpha. So you get the same conclusion here and here. So if h is the vertical height, if s is the magnitude of the linear displacement of the block up along the inclined plane, and h is the corresponding vertical height through which the block rises against the force of gravity, then sin alpha you can write h by s. Then work done by the gravitational force on the body can be written as from this equation mg of sin alpha. Sin alpha is h by s, that is minus mgh. So whenever the center of gravity of a block of mass m, suppose rises through a vertical height h near the earth's surface, we can say that work done by the gravitational force on the body is minus mgh, irrespective of the path followed. In some of the problem, the body may rise vertically upwards. For example, the body may be moved up along the inclined plane. Where in another problem, the body may move up along the curved path. In another example, the block suspended by a string may rise through vertical height. So irrespective of the length of the path followed or type of the path followed, whenever the center of gravity of the body rises through a vertical height h near the earth's surface, work done by the gravitational force of the body can be written as minus mgh if h is very, very small compared to the radius of the earth. And whenever in those problems when the center of gravity of the body falls through a vertical height h near the earth's surface, that means the body comes near to the earth's surface through a vertical height h, then work done by the gravitational force on the body will plus mgh irrespective of the path followed. Because in a good number of problems we have to calculate work done by the gravitational force of the body. So here now I am going to show you the same conclusion on the screen. Those who are writing the notes, they can again restart writing. I have shown you the conclusion on the screen, which I have just now discussed. That is the notes for what I have discussed just now. Those who are writing the notes, come on. Again, they can restart writing. I will read out this. When the center of gravity of a body of mass Kepler falls to a vertical height h near the Earth's surface, then the work done by the force of gravity on the body is given by W subscript small g equal plus mgh. Of course, when h is very, very small compared to radius of the Earth, irrespective of the path followed by the body. That means irrespective of whether the body moves vertical path or inclined path or any other path or curved path. Come on, those who are writing the notes, please finish writing this point. So in case you need more time to copy this, you can take a pause. You see the next one. When the center of gravity of the body rises to a vertical height h near the Earth's surface, and the work done by the gravitational force of the body is given by W subscript small g equal to minus mgh, irrespective of the path followed. Come on, copy down this point also. I mean, those who are writing the notes, please copy down this point also. So you must be familiar with units of work in the school syllabus itself, but still I once mention, as you know, probably unit of work in a SI system is joule. Unit of work in any system is equal to unit of force into unit of displacement in the same system. Unit of force in a SI system is Newton, unit of displacement is meter. So we can write 1 joule is equal to 1 Newton meter, or the symbols we write this way. So that means when a force of 1 Newton acting on a body gives a displacement of 1 meter in the direction of the force, then the work done by the force is said to be 1 joule. In the series system, unit of force is dyne, unit of displacement is centimeter, and unit of work is erg. Unit of work in any system, we can write unit of force into unit of displacement. So you can write 1 erg is equal to 1 dyne into 1 centimeter. As must be familiar with the conversion, 1 dyne you can write 10 power minus 5 Newton, and 1 centimeter equal 10 power minus 2 meter. So you get 10 power minus 7 Newton meter, and 1 Newton meter you can write 1 joule. So that is 10 power minus 7 joules. That means you can write 1 erg is equal to 10 power minus 7 joules. So next I would like to discuss one problem before I am going to discuss the term power. Look at the problem on the screen. A work W equal 100 joule was performed by a constant force F to lift a body of mass 2 kg vertically upwards when it rises through a vertical height of 2 meters. With what acceleration was the body raised with? So take g or 10 meter per second square. Come on, copy the figure. In case you want to try it yourself first, you can take a pause and try it. But of course, I am going to discuss this problem now. To find the acceleration of the body, you have to find the magnitude of the constant force F applied on the body. You are given work done by the force F. So work done by the constant force F when the force acts in the direction of the displacement is given by product of the magnitude force and magnitude displacement. Or if you use the formula F cos theta, here the angle theta between force F bar and displacement S bar is 0 degrees. So here work done is 100 joules. That is given in the problem. Magnitude of the displacement is 2 meters. Cos theta is 1. So you get magnitude of the force. From this you can simplify it. You get 50 Newton. To find the acceleration, we have to apply Newton's second law. F represents the magnitude of the constant force applied by an external agent which acts in the direction of motion. The weight mg of the body acts vertically downwards, opposite to the motion. So magnitude of the resultant force on the body in the direction of its motion. Can write F minus mg. Here F equal to 15 newtons. The mass of the body is given as 2 kg. G is given as 10 meter per second square. So magnitude of the resultant force on the body will be equal to 30 Newton. From Newton's second law, the magnitude of the resultant of all the external forces acting on the body will be equal to the product of its mass and acceleration. So magnitude of the resultant force is equal to 30 newtons. The mass of the body is equal to 2 kg. Therefore, magnitude of the acceleration will be equal to 15 meter per second square. That's the answer. So if you want to copy down the solution of this problem, you can take a pause and copy down the solution of the problem. Next, I am going to discuss the term power. So all of you please stop writing, you just concentrate only to listen. I am going to discuss the term power. Don't write running notes while I am discussing. I will be showing you the notes separately for you. So those students who want to write the note, they can write the notes later. Now just listen. As you might have already heard about these terms, work, power, energy, in the school syllabus also. So come on, you tell me what is power and what is the basic formula which we use for calculation of power for problems in physics. So when I ask the same question in the class, of course, most of students will say power is the rate of doing work or work done per second. When I ask them what is the formula for power, they say P equal to W by T. Then I ask the students, what do you mean by W? So we say, most of students say work done. So again I ask you, does W denote work done by one of the forces acting on the body or work done by the resultant force of the body? Again I repeat my question. Does W denote work done by one of the forces acting on the body or work done by the resultant force on the body? I mean, the body may be under the action of more than one force in most of the problems we deal. So what many students usually tell me, the W represents work done by the resultant force of the body. Now see, let us consider one example. Please don't copy all this discussion. I will show you the notes later. At present, you just please only concentrate to listen. Let us consider an example. I'm not solving a problem, only are discussing here one simpler situation. Let us suppose a block of mass m is dragged along a uniform rough horizontal floor by applying some pulling force at some angle theta above the horizontal. Let us suppose the block is moved with constant velocity. Here Fa bar represents the force applied by a pulling source or person or object or body, whichever applies the pulling force. We call it as agent. Agent means the body or person or mission or engine or whichever applies the pulling force on the block. We call it as agent. Let us suppose the block is moved along the rough floor with uniform velocity. Of course, the other forces which act on the block are force of sliding friction by the floor, which acts opposite to the direction of motion of the block. So weight mg acts downwards, normal reaction force upwards. Suppose if the magnitude of the pulling force is adjusted so that the block moves with a constant velocity. Suppose if the block moves in a straight line path with uniform velocity, then what is the acceleration of the block? So you must be able to tell acceleration of the block is 0 or magnitude of acceleration is 0. Magnitude of the resultant force. What is the magnitude of the resultant force of the body from Newton's second law? Product of mass and magnitude of the acceleration. So acceleration is 0, magnitude of the resultant force of the block is also 0. Then what is the work done by resultant force on the block? If the block is suppose moved with constant velocity along the rough horizontal floor. So when the resultant force of the block is 0, work done by resultant force will also be 0. What is the power in this example? Some of you may say 0, but it's not 0. The power in this example, same special case, we'll discuss similar situation later in problems also, will be given by Fa into V cos theta. Or Fa is the magnitude of the force applied by the agent, or Fa bar dot V bar. Theta is the angle between F bar and V bar, Fa bar and V bar. See, when we just use the term power, it does not give a complete meaning. You must also mention about the agent. That means power of whom or power of what. You are talking about the power of which agent or which person or body or agent you must mention. So more clear formula for calculation of average power, you can say like this. This is the main formula. Of course, don't write the notes now. I will show you the notes later. So average power delivered by an agent can be written as equal to work done by the agent divided by time interval. So average power delivered by an agent is equal to work done by the agent divided by time interval. So work done by the agent need not be equal to work done by the resultant force of the body. Of course, there are some problems where work done by the resultant force of the body may become equal to work done by the force applied by the agent of the body. For example, when the block is moved along a smooth horizontal floor by applying a pulling force at some angle theta above the horizontal, So in this case, work done by the resultant force of the body may be same as the work done by the pulling force applied by the agent of the body, but not in general. So in general, average power delivered by agent should be written as work done by the agent, means work done by this force applied by the agent on the body divided by time interval. So you should not write average power delivered by the agent equal to work done by the resultant force divided by time interval. Should write work done by the force applied by the agent on the body divided by time interval. So in general, average power delivered by an agent is equal to work done by the force applied by the agent on the body divided by time interval. So when we consider an infinitesimally small time interval denoted by dt, then the average power for the infinitesimally small interval of time dt, we call it as instantaneous power. So coming to the term instantaneous power, so let dW subscript A denote the work done by the force applied by the agent of the body for infinitesimally small displacement dr bar. That we can write F bar subscript A, F subscript A represent the magnitude, F subscript A represents the force applied by the agent of the body. So work done by the force applied by the agent of the body when the body undergoes infinitesimally small displacement dr bar, let FA bar dot dr bar. So instantaneous power output of the agent, we may denote P subscript I, is equal to the average power during the infinitesimally small interval of time dt. So the power delivered by the agent may be constant in some examples, may not be constant in some of the examples. So, but in the general case, so if the power may or may not be constant, therefore we write instantaneous power as dWA by dt. dWA is the work done by the agent for the infinitesimally small interval of time dt. This you can write F bar dot dr bar, or instantaneous power output of the agent. You can write FA bar dot V bar, where V bar equal to dr bar by dt represents the instantaneous velocity of the body. So here F bar dot V bar, in some of the books they simply write as F bar dot V bar. Remember that F bar represents the force applied by the agent. Should not be taken to be equal resultant force in all the examples. So of course if the power is constant, in some problems and examples which we may discuss later, power may be constant. In that case, instantaneous power will be equal to the average power for a finite time interval. So in the general case, instantaneous power we write FA bar dot V bar, or we can also write FA V cos theta, where theta is the angle between F bar and V bar, FA bar and V bar. So you must be familiar with the units of power, as you might have studied in the school. Unit of power SI system is named in honor of the scientist by the name James Watt. So power of an agent is said to be 1 watt if 1 joule of work is done by the agent at in each 1 second. So unit of power you can write unit of work by unit of time. So 1 watt you can write 1 joule by 1 second. Or in symbol we write watt by capital W, joule by capital J, second by small letter S. So 1 horsepower can be defined as the power of an agent which works at the rate of 746 watts or 746 joule per second, or 1 horsepower in short we write HP, that equals 746 watt. So coming to some cases in calculation of power, so coming to the discussion about some special cases in power. Suppose we consider the most simpler case where the body is moved in the horizontal direction or it may be moved along an inclined path with uniform velocity. So we are not solving any problem at present. We are only discussing some of the special cases in calculation of power. So if the force applied by the agent to the body is suppose constant and acts in the direction of the motion of the body is moved with uniform velocity. The body may move along the horizontal floor in some of the problems. In some of the problems, the body may be moved up an inclined path, which may have an angle alpha with the horizontal. In that case, force is constant, velocity is constant in this case. So instantaneous power F bar dot V bar is constant. So in this case, instantaneous power will be same as the average power. The magnitude of displacement of the body when the body moves with uniform velocity, you can write SV into Vt. And work done by the force applied by the agent to the body. When the force applied by the agent to the body acts in the direction of displacement, you can write product of magnitude of the force applied by the agent and magnitude of the displacement. Magnitude of the force applied by the agent is equal to V into T. Here S is the magnitude of the displacement covered in time T. So average power delivered by the agent for a time interval T is equal to the work done by the agent divided by time interval T. That is FVT by T. Or we write F into V. Or FA into V, I mean. So in the force F bar applied by the agent to the body acts in the direction of the motion and the body moves with uniform velocity, and power delivered by the agent you can write F into V. Of course, you can also arrive at this conclusion by the direct formula for instantaneous power F bar dot V bar, FA bar dot V bar. Here the angle between FA and F bar and V bar, I mean FA bar and V bar is 0 degrees. So you get FA into V. So the average instantaneous power will be same as the average power in this case. So coming to the another case, the constant force F bar acts, I mean that the force applied by the agent to the body is constant and acts at an angle theta with the direction of the motion of the body, and the velocity is also constant. Please don't write the notes now, we will be given the notes later separately at the end of my discussion. So in this case, the instantaneous power as we discussed earlier, FA bar dot V bar FAV cos theta. So they have to find the average power. Let us first find magnitude of displacement is given by again by same equation S equal to V into T. So in this case to here, the work done by the force applied by the agent on the body, you can write FA S cos theta. Theta is the angle between the direction of the displacement, direction of the force. Can write S equal to V into T. So average power delivered by the agent equal to work done by the agent divided by time interval. Here work done by the agent in time to you can write FVT cos theta. So the power we write FAV cos theta, which is same as FA bar dot V bar. That means average power is same as the instantaneous power even in case 2. So the conclusions are that in the case 1, that means when the force applied by the agent of the body acts in the direction of the displacement of the body, and the body suppose moves with uniform velocity, and the power delivered by the agent is simply given by a product of magnitude of the force applied by the agent and magnitude of velocity. The force applied by the agent is constant but acts at an angle theta with the direction of the velocity, and the body moves with uniform velocity v bar. And the power delivered by the agent, I mean average power, which is of course same as instantaneous power in this case, will be equal to Fv cos theta or F bar dot v bar. So coming to another case where the average power and instantaneous power may not be equal in some of the cases. Let us consider the case where a body starts from rest and moves with a constant acceleration. Here I am going to discuss about how to calculate the instantaneous power and average power. Suppose the body moves on a smooth horizontal plane. That means there is no friction here. The body moves on the smooth horizontal plane, there is no friction here. Let F bar denote the force applied by the agent of the body, which may act in the direction of the motion, or sometimes it may act at some angle theta with the direction of the motion. So in this case, work done by the resultant force, as I told you, when several external forces act on a body, work done by the resultant force will be equal to algebraic sum of work done by all the forces. That is work done by the force applied by the agent plus work done by the gravitational force plus work done by the normal reaction force. So if the body moves in the horizontal direction on a smooth horizontal plane, no work is done by the gravitational force on the body, and also no work is done by the normal reaction. Here Wn, I mean W subscript n represents work done by the normal reaction force on the block. W subscript G represents work done by the gravitational force of the block. W subscript A represents work done by the agent of the body. So work done by the resultant force, same as the work done by the force applied by the agent of the body, which you can write it as Fs cos theta. I mean if the body moves in a straight line path with uniform acceleration, magnitude of the displacement covered in time t, if it starts from rest and moves with constant acceleration, given by half at square. So average power delivered by the agent for a time interval t is equal to work done by the agent for a time interval t divided by t. That we write Fa into half at square into cos theta by t. So that is half Fa into at cos theta. So instantaneous power delivered by the agent given by F bar dot V bar. Fa bar dot V bar. That is Fa V cos theta. The body moves with constant acceleration in a straight line path, and final velocity of time t we write V equal to U plus Et. The initial velocity is 0, we can write V equal to A into t. So instantaneous velocity of a time t, we get V A into t. So you can observe that if you compare the instantaneous power with the average power, Fa into Vt cos theta by half F subscript A into V At, this is also A, should be written as A cos theta. That we get 2. That means instantaneous power after time t will be 2 times the average power for a time interval t. So that means in general, if a body is moved with uniform acceleration starting from rest along a horizontal plane or in the horizontal direction, then the instantaneous power will be 2 times the average power after a given time interval. So in the problems on power, you come across good number of problems in different books where you are asked to calculate the power in lifting a mass m through certain height h. So if a body of mass m is suppose lifted vertically upwards, in the absence of variations and friction, that means there are only 2 forces acting on the body. One is the force applied by the agent on the body, which acts in the direction of the motion. Gravitational force mg acts opposite to the direction of motion. The body is moved vertically upwards away from surface to the ground. So magnitude of the resultant force of the body is equal to magnitude of force applied by the agent minus mg. From Newton's second law, that you can write m into a. So magnitude of force applied by the agent in this case equal to m into g plus a. Let us suppose the force applied by the agent is constant, and the body moves with constant acceleration. So work done by the force applied by the agent, the body moves through a distance s is equal to fs cos theta. Here theta is 0 degrees. That is m into g plus a into s. So average power delivered by the agent is equal to work done by the agent divided by time. So m into g plus a into s by t. Suppose if the body moves with uniform velocity or with negligible acceleration and rises through a vertical height h, then we can write the average power delivered is equal to mgh by t. So I will continue my discussion in my next class.